The key to understanding why a great deal of energy is released in nuclear reactions is in the equivalence of mass and energy. Mass and energy are essentially the same. They're two sides of the same coin. Mass is like a super storage battery. It stores energy that can be released if and when the mass decreases. Consider the work that would be required to separate all the nucleons from a nucleus. Recall that work, which transfers energy, is equal to the product of force and distance. Imagine that you can reach into a U-238 nucleus and, pulling with a force, remove one nucleon. Then keep repeating the process until you end up with 238 nucleons, stationary and separated. You start with one stationary nucleus containing 238 particles and ended up with 238 separate stationary particles. Work is required to pull a nucleon from an atomic nucleus. This work goes into mass energy. The separated nucleons have a total mass greater than the mass of the original nucleus. The extra mass, multiplied by the square of the speed of light, is exactly equal to your energy input. E equals mc squared. One way to interpret this mass change is that a nucleon inside a nucleus has less mass than its rest mass outside the nucleus. How much less depends on which nucleus. The masses of the pieces that make up the carbon atom, 6 protons, 6 neutrons, and 6 electrons, add up to about 0.8% more than the mass of a C12 atom. This useful graph plots nuclear mass per nucleon from hydrogen through uranium. The mass per nucleon graph is an energy valley that starts at hydrogen, drops to the lowest point, iron, and then rises gradually to uranium. A proton has the greatest mass when it's in the nucleus of a hydrogen atom. The low point in the graph occurs at the element iron. This means that pulling apart an iron nucleus would take more work per nucleon than pulling apart any other nucleus. Iron holds its nucleons more tightly than any other nucleus does. Beyond iron, the average effective mass of nucleons increases. If a uranium nucleus splits in two, the masses of the fission fragments lie about halfway between uranium and hydrogen. The mass per nucleon in the fission fragments is less than the mass per nucleon in the uranium nucleus. When this decrease in mass is multiplied by the speed of light squared, it's equal to the energy yielded by each uranium nucleus that undergoes fission. The missing mass is equivalent to the energy released. Any nuclear transformation that moves nuclei towards iron releases energy. Nuclei that have atomic numbers greater than iron move toward iron by dividing, nuclear fission. Nuclei that have atomic numbers less than iron move toward iron by combining. The steepest part of the energy hill is from hydrogen to iron. Energy is released as light nuclei fuse or combine rather than split apart. This process is nuclear fusion. 2 protons and 2 neutrons have more total mass when they're free than when they're combined in a helium nucleus. Because atomic nuclei are positively charged, for fusion to occur, they must collide at very high speeds to overcome electrical repulsion. Fusion that happens because of high temperatures is called thermonuclear fusion. In the central part of the Sun, about 657 million tons of hydrogen are converted into 653 million tons of helium each second. The missing 4 million tons of mass is discharged as radiant energy. Producing and sustaining such high temperatures along with reasonable densities is the goal of much current research. No matter how much temperature is produced, a problem is that all the materials melt and vaporize at the temperatures required for fusion. One solution to this problem is to confine the reaction in a non-material container such as a magnetic field. A magnetic field is non-material, can exist at any temperature, and can exert powerful forces on charged particles in motion. Magnetic walls of sufficient strength can hold hot ionized gases called plasmas. Magnetic compression heats the plasma to fusion temperatures. At about 1,000,000 degrees, some nuclei are moving fast enough to overcome electrical repulsion and slam together, but the energy output is much smaller than the energy used to heat the plasma. At about 350 million degrees, the fusion reactions will produce enough energy to be self-sustaining. At this ignition temperature, nuclear burning yields a sustained power output without further input of energy. Fusion has already been achieved in several devices, but instabilities in the plasma have prevented a sustained reaction. A big problem is devising a field system that will hold the plasma in a stable and sustained position while a number of nuclei fuse. Fusion power is nearly ideal. Fusion reactors cannot become supercritical and get out of control because fusion requires no critical mass. There's no air pollution because the only product of nuclear fusion combustion is helium. Disposal of radioactive waste is not a major problem. The fuel for nuclear fusion is hydrogen, in particular its heavier isotopes, deuterium and tritium. Hydrogen is the most plentiful element in the universe. Deuterium and tritium are found in ordinary water. Because of the abundance of fusion fuel, the amount of energy that can be released in a controlled manner is virtually unlimited. The development of fusion power has been slow and difficult, already extending over 50 years. It's one of the biggest scientific and engineering challenges that we face. Our hope is that it will be achieved and will be the primary energy source for future generations.